Hello good people, I'm going to talk about the Lewis definition of acids and bases. Before I do that, allow me to remind you of the two previous definitions of acids and bases. The Arrhenius definition looked at what ions are generated in aqueous solutions, either hydrogen ions for acids or hydroxide ions for bases. The Bronsted-Lowry model followed the movement of the hydrogen ions. They were either being donated by acids or accepted by bases. These are good definitions. There is nothing wrong with them. However, once you get to know chemistry, once you get really close to it, and I mean eyeball to eyeball, you start to see that we really need to follow the electrons. More specifically, we need to pay particular attention to the valence electrons. They are the ones that will determine the reactivity of an atom. Let me look at an example acid-base reaction. Here we have hydrochloric acid reacting with water to give a hydronium ion and a chloride ion. If I'm going to talk about the Lewis definition of acids and bases, I need to represent the reactants and products using Lewis dot structures. So what has happened in terms of valence electrons? A lone pair of valence electrons from the water molecule, the base in this case, is being donated to the acid. In effect, this means that the water molecule is going to pinch the hydrogen of hydrochloric acid. That lone pair of electrons that was used to grab the hydrogen is this one here. We have generated a hydronium ion, also known as protonated water. Because water has grabbed a proton which carries a positive charge, the entire hydronium ion is positively charged. What has happened to the chloride of hydrochloric acid? Well, it got to keep the electron from the hydrogen, which means it has one extra negative charge, and therefore the chloride ion is negatively charged. What does this look like when we use lines to represent the bonds between the atoms? Well, it would look something like this. The blue curved arrow once again represents the direction in which the electron pairs are moving, from the base to the acid. And this brings us to the definition of Lewis acids and bases. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. In the case of hydrochloric acid and water, the water acts as a base and it donates an electron pair. The acid will accept the electron pair, and in the process, a hydrogen will change its residence, giving us a hydronium ion with a positive charge and another anion with a negative charge. Let me look at one more example. This time we have water and ammonia reacting to give ammonium and hydroxide ion. Note that in this example, water is the acid and ammonia is the base. In terms of Lewis dot structures, ammonia as the base will donate a lone pair of electrons to the water, which will be acting as an acid. Once again, the effect is that ammonia will essentially pinch a hydrogen, and we will end up with a positively charged ammonium ion and a negatively charged hydroxide ion, which has kept the electron of the hydrogen that got pinched. If we were to represent the bonding electron pairs with lines, it would look something like this. Here too, we would indicate that the lone pair of electrons on the ammonia would be donated to the water molecule. More precisely, the lone pair of electrons will be used to pinch one of the hydrogens of water. Before I finish this exciting video, I just want to draw your attention to the fact that the Lewis definition does not make the Arrhenius and Bronsted-Lowry definitions incorrect. It builds upon them. A base is still generating a hydroxide ion in an aqueous solution, meaning that the Arrhenius definition holds. A base will still accept a proton, which means that the Bronsted-Lowry model holds. But now we are looking at what the electrons are doing. A base will donate an electron pair, whereas an acid will accept an electron pair. That is all for now, and I will see you on the flip side.